In my previous video, we know that Gibbs entropy is less than or equals to Boltzmann entropy. Here, we can have a journey from Gibbs entropy through to Boltzmann entropy by optimizing, but now with constraint. Example in my video. But did you ever hear about canonical ensemble? But wait. What is actual canonical and ensemble? Definition of ensemble in physics here is about idealization that make representation to overall may infinitely many objects in our system. And of course, the word infinitely many object here is concerned in statistical mechanics. And next, about canonical itself, about what we know is some kind of rule of thumb, maybe? Something like that. So canonical ensemble itself is about rule of thumb collection of systems that we idealize one representation. In statistical mechanics, we have three kinds of canonical ensemble. First, we have microcanonical ensemble, which here, overall of infinitely many body in our system can be represented as isolate system. So here, each object will have E is constant measurement, and then we have N as constant measurement, and the last one we have volume as constant measurement, just like in first law of thermodynamics. Then by Lagrange multiplier method for maximum entropy with constraint, we have this difference, such here I some kind delay the equals 1 because its only probability is equals to 1. Each object has constant energy, constant total of number, and total of volume, so I don't have any constraint, which by the same method as my previous video, we will have this equality. And of course, the final result for probability I distribution, we have this equality, which inside of this equality is a constant. And notice that here, a constant probability will relate to this, which in my video, this thing will coming in Boltzmann entropy. Next, we have canonical ensemble, which has the same set of microcanonical before, but now we have closed system, which means each object has M that stay constant, T that stay constant. I mean here we can transfer energy, but now particle doesn't go out, and by the heat transfer possibility, we now have the system is touching reservoir, and of course the volume stay the same. And by the same procedure before, we have Lagrange multiplier is about this equality, because now we can transfer energy, we need to bring the energy conservation constraint set like this better. And by same procedure as before, we will have probability distribution at I state is about this, which we can have same procedure as before by normalization to find the specific form. And the last one here is about grand canonical ensemble. Same as before, but now we have open system, which here we can transfer energy and transfer matter. So the constant here is about temperature, that touching reservoir as before, the volume stay the same, and the third we have additional such mu I or just potential for each n I particle stay the same. And yeah, by the Lagrange method, we will have this equality, which we have constant in probability, total particle, and total energy as fundamental conservation law. And by the same procedure, we will have the distribution of probability Pi is about this equality, which we can try same procedure as before, such as normalization and etc. And last one, if we analyze the three results before, we see that in microcanonical, omega depends on total energy because each particle has same total energy, and for canonical ensemble part, we can determine this part, Z partition function, as in my video. And the very last, we can do the same thing to grand canonical ensemble, and that's how physics idealize our infinitely many body system.